Hello everyone, welcome to this video. In this video, we'll be looking at 4 examples of cyclic group. So here, let's see the fourth example. In this example, we are saying a group of complex numbers under the operation of addition that forms a cyclic group, and here the generators would be the number 1 and the number iota, because when you have the number 1 and when you have the number iota, then you can multiply this with any integer a, and you can multiply this iota with any integer b, and then you can add them so that this will form whole of the complex numbers, right? So they form whole of this complex number set under the operation of addition. So this is a cyclic group. Another example here is that of a group which is known as a group of Gaussian integers under the set of the real numbers, right? So here we have the number as 2, the number as pi, and the number as square root 2, right? These three numbers, 2 is a real number integer, pi and square root 2, they are irrational numbers, right? So here this their linear combination, so that means if we take three integers a, b and c as three integers, then 2a plus b pi plus c square root 2, that forms a cyclic group, and this group is called the Gaussian integers in the set of real numbers, right? So this is also a cyclic group. Let's see another example, example 6. So here the set Zn, we have already seen that the set of integers under addition forms a cyclic group with the generators 1 and -1. Now for the set Zn, which is the set of integers modulo n, right? So it will contain all the numbers starting from 0 to n-1, where n is greater than equal to 1. This is a cyclic group under the operation of addition modulo n, right? So here the number 1 and the number -1 is basically under the addition modulo n. -1 represents nothing but n-1, because as such -1 is not present. So this is a cyclic group because you start from 0, then you have 1, then you have 2, and you move forward like this, and finally you would have n-1, and then the next digit would be 0 only. So you see this forms a cyclic group like this, and moreover it has generators 1 and -1. And you should note that unlike the set of integers which only have two generators 1 and -1, this set of addition modulo n could have many generators. That will depend on what n is given to you, right? For an example, let's see the case of Z8. So for Z8, you know the set is given by 0, 1, 2, 3, 4, 5, 6 and 7. So this forms a cyclic group. Here you see 1 is a generator of this set, 3 is a generator of this set, 5 is a generator, and 7 is a generator. However, you do not have 0, 2, 4 and 6 as its generators, right? So let's see how this 3 is a generator. So you see the cyclic subgroup 3, that would contain the powers of 3 under the operation of addition, right? Addition modulo 8. So that means it would contain the elements like this: 3, 3 plus 3, 3 plus 3 plus 3, and so on. So it would contain the elements like this: 3 mod 8, that is 3 only. So this is 6, 6 mod 8 is 6 only. Then it is 9, 9 mod 8, that is equal to 1, right? 9 mod 8, that is, when you divide 9 by 8, you will get the remainder as equal to 1, right? So this is 1. Next element would be 3 plus 3 plus 3 plus 3. So this is equal to 6 plus 6, that is 12. So 12 mod 8, that is going to be equal to 4. So you see the next element is 4. And so when you keep on taking this power of 3, so that means when you keep on adding 3 to the next digits, you get all the elements of Z8 back. And after certain digits, after this 8 additions, the next addition would nothing be but the number 3. Next would be 6, and this would keep on going like this. Therefore this is a cyclic group. So here in this case, 3, the digit 3, that is a generator of the group Z8. However, 2 is not a generator. So let's see how this is the case. 2 is not a generator because the cyclic subgroup 2, that would contain the digits as 0, 2, 4, 6. Next 8 would again 8 mod 8, that is equal to 0 only. So you see we have again after 6 the value 0, then 2, then 4, then 6, and then 0. So this is not equal to Z8 because the elements 1, 3, 5 and 7 are missing from it, right? So I hope you understood this example. Let's see an example which is not a cyclic group under the operation of multiplication modulo 8. So let's say we take this group of integers under multiplication modulo 8, right? So it would have all the integers which are less than 8 and which are relatively prime to 8. So we have the number as 1, we have the number as 3, we have the number as 5, and we have the number as 7 within it. And the operation is multiplication modulo 8. So here this group is not a cyclic group. Why? Because if let's check that whether 1 is a generator or not. So when you take the powers of z, so that means you are multiplying 1 with itself. So 1 mod 8, that is equal to 1 only. 1 into 1 mod 8, that is again equal to 1 mod 8, that is equal to 1 only. 1 into 1 into 1, that is also 1, which is 1 mod 8 is 1. So you see you have only the element 1 within the set which is generated by the number 1. So therefore this is not equal to U8. So therefore this does not form the generator of the groups U8. Next, let's see about 3. So you have 3 mod 8 as equal to 3. Next, 3 into 3, that is 9. So 9 mod 8, that is equal to 1. 3 into 3 into 3, which is equal to 27. So 27 mod 8, it is equal to what? It is equal to 3, right? Because we have 24. So when you divide 27 by 8, you have here it will go by 3, it will be 24, and you have 3 as the remainder, which is the answer. So you see, next 3 into 3 into 3 into 3, which is 81. So 81 mod 8, that is equal to 1. So you see you have only the numbers 3 and 1 oscillating and repeating. So the set which is generated by 3 would contain only 3 and 1. This is also not equal to U8. What about the digit 5? So when you see the digit 5 here, so in this case we would have, for the digit 5, for 5 mod 8 is 5 squared, so 5 into 5, which is 25. 25 mod 8, that is 1. So next is 5 into 5 into 5, so that is 125. 125 mod 8, that is equal to 5, right? And we keep on doing like this. We have only two numbers, that is 1 and 5, present in the subgroup, in the set where this subgroup is formed by the element 5, and the next set is that generated by 7. So you see 7 mod 8 is equal to 7. 7 into 7, that is 49. 7 into 7, that is 49 mod 8. 49 mod 8 is you have 1, because 48 goes by 8. 7 into 7 into 7, right, that is 343 mod 8. So that is equal to 7, right? You can divide 343 by 7, right, and then see the results. It will go by 428, right, 63, right? So we have to, in order to take 343 mod 8, what we have to do, we have to divide 343 by 8, right? So when you divide 343 by 8, let's see what do we have. It goes on 4, so it is 32. We are left with 23, and 23 goes on 2, right? So it is 16. So when you subtract 16 from 23, it is going to be 7. So you see we have 7 1 7 1 7 1 and so on. So this is also not equal to u8, this is not equal to u8. So in every case, if for every element a which you take from u8, the set which is generated by a is not equal to u8, hence u8 is not a cyclic group, right? So I hope you understood what is a cyclic group with these bunch of examples. Well, that is it for this video. Thank you for watching.